everybody. Welcome to Calculus 3. This is a great course. I like it a lot. We're going to be learning ways of expanding on what we've already learned. So we're going to take concepts from Calculus 1 and 2, and we're going to carry those concepts forward into three-dimensional space. So instead of just working in X and Y, we're going to be working in X, Y, and Z, maybe even higher dimensions at certain points. Okay, so I think what makes this class challenging is the difficulty of trying to visualize three dimensions and draw those on a two-dimensional space. So that's not a terribly easy thing to do. It's difficult, especially if you're drawing by hand, to keep the perspectives correct and that kind of thing. So I want to recommend GeoGebra 3D to you. So if you haven't used this before, it's a great resource. It's a wonderful 3D grapher. It's free. You can graph your surface or whatever it is you're working with, and you can manipulate it, move it around, look at it from different angles, that sort of thing. For 2 dimensions, I highly recommend using Desmos Graphing Calculator. It's one of the best graphing calculators I've encountered. Absolutely love it. You can do 3 dimensions in Desmos. It is more challenging. It's a little more difficult. So I do recommend the GeoGebra for that. Okay. All right. So let's jump right in. We begin in chapter 11, which is all about vectors and space. Vectors and space. And space, by space we mean three-dimensional space, or double bar R cubed. So double bar R for the real numbers, cubed because it's 3 dimensions, so X by Y by Z. Okay, and we begin in section 11.1, which is learning about vectors in general, their properties, etc. But we're going to stick to the plane for now. So we're going to get to know vectors a little bit, kind of see how they work, and then we'll take those into 3 dimensions and work with them there. All right. So what the heck is a vector? Well, a vector is the set of all equivalent directed line segments. Okay, so first of all, what the heck is a directed line segment? It's exactly what it sounds like. Okay, so I'll call that DLS for short. A directed line segment is a line segment line. No, not even close. Try that one more time. Line segment that has magnitude and direction. Okay, that magnitude is a scalar. So let me write this down. Magnitude, also known as, so AKA for also known as, the length of the vector, length of the directed line segment, or the norm of the directed line segment. Okay, so the magnitude is a scalar value. In other words, it's a real number value. Okay, so for example, velocity is a directed line segment. Right, so velocity is a directed line segment. The magnitude of a velocity would be the speed. Right? So I could say, yeah, I'm driving south 50 miles per hour. Okay, great. I'm driving south 50 miles per hour. I have direction, I have a speed. That's a directed line segment. I could just say, oh, I'm traveling on this road that runs north-south at 50 miles per hour. You don't know if I'm going north. You don't know if I'm going south. But you do know I'm traveling at 50 miles per hour. So that is my magnitude, right? So just an example to help you kind of understand that if you've not dealt with vectors before. Okay, so in order to be equivalent, so 2 directed line segments are equivalent if they have the same magnitude and direction. Okay, so that makes them equivalent. And vectors, a vector, so a vector is the set of all equivalent directed line segments. Okay? Okay, so notation. So a directed line segment, PQ, is going to be the directed line segment running from point P to point Q. So we've got point P running to point Q. So P is our initial point. Q is our terminal point. Okay. That's a directed line segment from P to Q. So we could say that vector V is equal to directed line segment PQ. So you'll notice how similar, well, it's the same notation, right? You have this written. The difference is that here it's one letter, so I'm not telling you where it starts and ends. I'm just saying this is the vector V, whereas here I am telling you where does it start and where does it stop. Okay, this vector V is going to be the set of all vectors that have the same direction magnitude as PQ. Okay, so V is the set of all vectors with the same direction and magnitude as the directed line segment from P to Q. Okay? All right. Vectors can be broken down into what we call the component form. So let me write this down. Component form of a vector. Okay. This is just saying, well, to get from point P to Q, how far did we have to move in the x direction and how far did we have to move in the y direction? This is kind of what we're doing. So we're going to break down into the x and y components. So suppose I have got some vector moving from point P in the plane to point Q in the plane. And this is going to be my x-axis. This is going to be my y-axis. How would I get from point P to point Q if I couldn't walk in a straight line? If I could only walk parallel to the x-axis or parallel to the y-axis, how would we get there? Well, what we would do is we would walk until we're directly underneath Q. So we're going to begin at P. We're going to walk parallel to x until we are directly beneath Q. Then we are going to walk straight up until we reach point Q. So the yellow here is my x component, and the vertical is the y component. Okay, and the magnitude of these little directed line segments here is the x component and the y component. So we could represent our vector V. So assuming that PQ here is vector V, I did not want that in green. Back to white. There you go. So this is vector V, PQ. We would write V equal to, and we're going to use corner brackets here, x component, y component. Okay, so we call that V1, V2. So the x component is V1, the y component is V2. Okay. Now the nice thing about this is if we were to relocate this vector so that it started at the origin, try to make the same vector with the same magnitude and direction, then if this is point xy, the components are simply x, the x value, and the y value. Those are our components. So here we have our vector V equal to xy. Okay, so that's very nice. If I give you, say this is x and this is y, and I give you a vector that begins at the origin and ends at 0.32, right? The vector from the origin to that 0.32 is simply 3, 2 with the corner brackets. Okay, so that's nice. Very straightforward, very simple. Okay, okay. The zero vector. The zero vector, which is denoted 0 with the vector line above it, or in component form 0, 0, this is a vector that has no magnitude. Vector with 0 magnitude. Okay, so it's an interesting vector because it has no direction. It doesn't go anywhere, right? So it's the only vector that really doesn't have a direction because it has 0 magnitude. So it doesn't really go anywhere. Okay. Now, suppose I have got two vectors u and v. All right. So these will be my equivalent vectors. So given u in component form u1, u2, and v in component form v1, v2, these are equivalent if u1 is equal to v1 and u2 is equal to v2. That's how it's equivalent. If the components are equivalent, the vectors are equivalent. All right? All right, so how do we calculate the magnitude of a vector? Well, it's pretty straightforward. Suppose I have a vector. Let's use 3, 2 again. So here's my vector. V is equal to 3, 2. Well, we can break that down into its components. And the x component and y component are always perpendicular to each other. Therefore, they form a right triangle when we draw them in. So now we have a right triangle. So my right triangle looks something like this. 3 is the horizontal leg, 2 is the magnitude of the vertical leg, and the hypotenuse here we can calculate using Pythagorean theorem. So this is going to be the magnitude of vector v. All right. So using Pythagorean's theorem, we have the magnitude of vector v is equal to, squared, is equal to the sum of the legs squared. So 3 squared plus 2 squared. All right, so we're going to take the square root of both sides, and we get the magnitude of vector v is equal to plus or minus the square root of the 3 squared plus 2 squared. However, this is a magnitude. I'm not interested in direction at all. I don't need positives or negatives. I just need the absolute value. So we don't need the negative, positive only. Okay, so magnitude is a type of absolute value, right? Okay, so the magnitude of v then is equal to the square root of 3 squared plus 2 squared, which is the square root of 9 plus 4, which is the square root of 13. So the magnitude of vector 3, 2 is square root of 13. Okay, so now let's generalize that. Suppose I have two points in space, PQ, okay, and P is the point P1, P2, and Q is the point Q1, Q2. Let's see if we can calculate that magnitude. So let's draw in our x component and y component. Okay, so what is the x component here? Well, the x component is going to be Q1 minus P1. Okay, so that's my x component. And the y component is Q2 minus P2. So Q2 minus P2. These are our components. So PQ is equal to Q1 minus P1, comma, Q2 minus P2. All right, so there we have it. Those are the lengths of the x component and the y component. Those are their magnitudes. So if we want to find the magnitude of vector PQ, we can use these components to say, well, that's equal to the square root of the x component squared plus the y component squared. And there we have the magnitude of any vector PQ. Okay. Alrighty. In component form, if we have vector v equal to v1, v2, then that implies that the magnitude of v is simply the square root of v1 squared plus v2 squared. All right, so it's the same thing here. Okay, now some special terminology. If the magnitude of a vector is equal to 1, we call it a unit vector. Is a unit vector. Okay, think of the unit circle. Probably seen that before. If I've got the unit circle, pick any vector and put it on here. Any vector with magnitude 1 is going to stop right there on the unit circle. All right. So what are the components here? Well, for every point on the unit circle, the point of that is cosine of theta, sine of theta, right? So any unit vector, so every unit vector can be represented as, let's call it u for unit vector, u equal to cosine of theta, sine of theta. Those are the components, right? The x component and the y component. So that's a unit vector, right? Now, we can multiply these by a scalar to make it longer or to make it shorter, right? So if we have, let's say a scalar c, so let c be a real number, then c times our unit vector is equal to c times the vector in component form. Okay? And we just have this becoming c times the cosine of theta and c times the sine of theta. And that's actually one of the properties of vectors. It's called scalar multiplication. All right, so let's look at that now. Let's look a little closer at that. So let's look at some properties of vectors. Okay, we're going to let u be the vector given by u1, u2, and v the vector in component form v1, v2. Okay, and c and d are going to be real numbers, so in other words, they are scalars. If that's the case, then we have the following. The sum of two vectors, u and v, is going to be the sum of their components, u1, v1, u1 plus v1 and u2 plus v2. Okay. Next, the scalar multiple. This is what we just saw. C times u is just the vector c times u1 and c times u2. So that would be in component form. Okay. The opposite of a vector is just going to be the same as multiplying -1. So it's going to be like multiplying the scalar -1. That's going to be the opposite of v1, opposite of v2. So it's going to be moving in the exact opposite direction. Okay. The difference of u minus v, that's going to be equal to u1 minus v1, u2 minus v2. Just like adding a negative, right? So it's like u plus the opposite of vector v. So if you want to think of it in that way. Okay. All right. We can do a lot of this geometrically. So for example, if I wanted to combine vectors u plus v, so suppose I've got vector u here and vector v here. If I wanted to add u plus v, we can do that by taking v and adding it to u. So u stops here and then I would draw V right there. Okay, so this is in a way breaking it down into components, not into the components in the x direction and y direction, but kind of like saying, oh, well, you know, I've got components u and v. What is that going to give me when I put them together? And what it gives us, I can get my color, it gives us this combination right here, u plus v. Okay, so to add vectors geometrically, you simply place the tail of the first vector, the tail of the second vector to the tip of the first vector, and then draw the line between them. Okay, all right, so there's that. Now, let's see here, the difference in two vectors. Doing this geometrically, so suppose I'm going to use the same u and v. So u comes out like this, v comes out like this. Okay, so the difference in two vectors, probably the easiest way to think about this, is simply to think of it as adding the negative. So if v is here, the opposite of v is going to move in the exact opposite direction, but it's going to have the same magnitude. So then we can add the opposite of v to u. Okay, so at the tail here of u, we're going to, or tip to tail, we've got v here. All right, or I'm sorry, that's the opposite of v, that's negative v. We put those together, we draw the line connecting the end of u here to the top of v, negative v, and we have u plus negative v, which is u minus v. Okay, so this is one way that we can do that. Another way that we can do that is to take u and v, go back to white. So here's u, here's v. Okay, we can take u and v and we can draw them nose to nose, like tip of the arrow to tip of the arrow. So let's draw v right over here. Okay. Then I'm going to connect u to v. Okay. And we get the exact same vector. Okay, and then another way we can kind of look at this subtraction business, we've got u and v, so there's u sort of, there's v sort of. Just put them to where they are at initial point to initial point, and then just draw the vector from v to u. Because we're subtracting v from u, we're going to draw the vector from the terminal point of v to the terminal point of u. And again, we get the exact same vector. So we have u minus v here, we have u minus v here. So several different ways we can kind of think about that geometrically. Personally, my favorite is thinking of it as adding the negative, because adding vectors, for whatever reason, is so much more intuitive than subtracting them. So if we just add the opposite, that's what we'll get. So this is how I would recommend thinking about subtraction of vectors, is just adding the negative. Okay, all right, so a few more properties of vectors. So more props of vectors. All right, so we're using the same u, v, c, and d here. If I have got vector u plus vector v, that is the same as vector v plus vector u, right? So addition of vectors is commutative. It's also associative. If I've got u plus v and then I add vector w, that's the same as if I have vector u plus vector v plus vector w. Okay, u plus the 0 vector is just the original vector u, so that's our additive identity. If I were to add the opposite of a vector to itself, we get 0, so there's our inverse property of addition for vectors. Scalar multiplication, so suppose I've got scalar c times d times vector u. That's the same as c times d times vector u. Okay, same thing for adding the scalars. So if I've got c plus d, I shouldn't say same thing, but if I've got c plus d times u, that's equal to c times u plus d times u. Okay, so the distributive property holds. It holds for scalars and for the vectors. So suppose I have a scalar times the sum of two vectors. That's going to be cu plus cv. Okay, and finally, if I have a scalar of 1 or 0, if I multiply by scalar 1, looks like a 1 times vector u, that's just vector u. And if I multiply the 0, 0 times vector u, I get the 0 vector. Okay, so if we multiply by 0, we get the 0 vector. All right, so this video is running a little bit long. I will try to keep these under 20 minutes in general, but I think we're getting closer to the end of this, so let's go ahead and wrap it up, get the rest of this on here. Let me give you a theorem. So theorem 11.2, all those lovely properties are the theorem 11.1. The length of a scalar multiple, the length of a scalar multiple. So if I've got v, vector v, and let v be a vector, and c a scalar, and that's c is a real number. Okay, so c a scalar, then the magnitude of c times vector v is equal to the absolute value of c times the magnitude of vector v. So let's see why that is. Let's do a quick proof of that just so you can see it. So our proof here goes like this. CV, right? So I've got a scalar times my vector v. We know that that's equal to c times, in component form, v1, v2. And from our properties, we know that that can be written as cv1, cv2. Now let's find the magnitude of that. So that's the magnitude of cv1, cv2, which is equal to, okay, so that's going to be the square root of cv1 squared plus cv2 squared. So it's the sum of the squares of the components. Okay, so that is equal to the square root of c squared v1 squared plus c squared v2 squared. Factor out the c squared. All right, and remember, so let me write this off to the side here. So recall, the square root of x squared is just equal to the absolute value of x. Okay, so this is going to be equal to the absolute value of c times v1 squared plus v2 squared. But v1 squared plus v2 squared, the square root, is the magnitude of vector v. So that's the absolute value of c times the magnitude of vector v. And there we have proven our case. So there's our we proved it party box. The end of our proof. Okay, excellent. All right, next theorem. So theorem 11.3, unit vector in the direction of v. In the direction of v. You can't see it, but I've got a color palette up in the corner that makes it hard for me to get to that corner. All right. So theorem 11.3, it says that if v is a non-zero vector in the plane, then u equal to vector v divided by the magnitude of vector v, which is really just 1 over the magnitude of vector v times vector v, right, has length 1 and the same direction as v. Okay, so in other words, it's a unit vector because it has length 1. So why is it the same direction as v? Well, take a look. Notice 1 over the magnitude of v is a scalar. The magnitude of v is a real number. It's a scalar. 1 over that number is also a scalar. So the reciprocal of the magnitude is just a scalar, and we have a scalar multiple of v. A scalar multiple is never going to change the direction. It's just going to make the vector longer or shorter. Okay? Alrighty. So let's do a quick example using that. Let's find the unit vector in the direction of v equal to, and let's do 6, -8. All right. Well, the unit vector is going to be equal to v divided by its magnitude. Okay. So v is the vector 6, -8, divided by the magnitude, which is the square root of 6 squared plus -8 squared. So that is 6, -8, divided by the square root of 36 plus 64. So that is 6, -8 divided by 10. Okay, well, we don't really think of dividing vectors, but we do multiply by scalars. So this is 110 times v, so 6, -8. So that's going to give me, what, 3/5, -4/5. And there is our normalized vector. So in fact, that's part of what this is called. So this process is called normalizing, because of the norm, right? Normalizing vector v. So we've normalized this vector. We have found its unit vector. Okay. All right. So one more thing to go over, and then we'll wrap this one up. I say one more thing, two more things. The first thing is the triangle inequality. So this is a big deal. It comes up all over the place in all kinds of proofs and things that you'll be doing in future classes. So the triangle inequality is very straightforward. Just says that the length of two sides of a triangle are at most, let me start over, sorry. The length of the sum of two sides of a triangle is going to be greater than or equal to the length of the third side, okay? So that's what that's saying. So suppose I have vectors u and v, and the sum of those two vectors, u plus v, okay? Then the triangle inequality says that the sum of the magnitude of u and the magnitude of v is going to be larger than or equal to the magnitude of u plus v. Okay, just makes sense. If the third side were longer than u plus v, then if I were to lay out something like u and v, right, and I got something like this, u plus v being longer, you can see here that there's no way for me to make a triangle. This is not possible. This is not a possible equivalence. So the very longest that third side could be would be if u and v went in exactly the same direction. Then the third side would just form a straight line here, and that would be u plus v. If I add any angle at all to u and v, then that third side is going to be shorter than the two of them, okay? So that is an extremely handy bit of information to have. And then, as promised, the last thing here are the standard unit vectors. Okay, so these are the unit vectors in the x direction and the y direction. Unit vectors in the x and y directions. All right, handwriting has deteriorated entirely. There we go. So the unit vectors in the x and y directions. So in the x direction, we call it I. Okay, so there's our I vector. It's the unit vector given by 1, 0. Okay, we move 1 in the x direction. We do not move in the y direction at all. Okay. In the y direction, That vector is denoted j, and it's equal to 0, 1. Okay? So we don't move in the x direction at all, but we move 1 unit in the y direction. Okay, so let's see here. Suppose I've got a vector v, and that vector is equal to the component, in component form, v1, v2. Okay, so there it is in component form. I could write that as the sum of two vectors. So I could write that as the sum of v1, 0, so moving in v1 in the x direction, plus the vector 0, v2, right? Because the first vector is solely in the x direction, the second vector is solely in the y direction. Okay, so then that's going to be equal to v1 times the vector 1, 0, right? Because if I were to distribute v1, I would get v1, 0. So it would take me right back to where I was, plus factor out the v2, 0, 1. But as we've just defined, I is 1, 0, and j is 0, 1. So we can write this as v1 I plus v2 j. So this is the standard unit vector form. Standard unit vector form. Because we're now writing it in terms of I and j. A scalar times I plus a scalar times j. So we're moving this much in the x direction, this much in the y direction. All right. So let's do one last example here, just so you can kind of see this in action. So we have got v equal to PQ, where P is the point to -5 and Q is the point -4, 1. All right. Then we are going to let vector U be equal to 2I minus j. Okay, and then we're going to write each vector as a linear combination of I and j. All right, so we're going to write as a linear combination, meaning adding it, linear combination of I and j. All right, so W. Vector W is equal to 2v minus 3u. All right, so let's take a look here. V was not given to us in component form or as a linear combination of I and j, so we need to do something to come up with that. So let's see here. V was PQ. So let's write that in its component form. So that's going to be Q1 minus P1. That's my x component. And the y component is going to be Q2 minus P2. Okay? So just to be clear where I'm getting these from, this is P1, P2, Q1, Q2. Okay? Alrighty then. So that's going to be -6, +6. So we have -6, 6 is v in component form. So as a linear combination of I and j, that's -6 in the I direction plus 6 in the j direction. So there's v. So now we're asked to find w. So w is 2v minus 3u. So that is 2 times -6i plus 6j minus 3 times u was given in the linear combination form, the standard unit vectors, 2i minus j. Okay. So that's -12 in the I direction plus 12 in the j direction minus 6 in the I direction plus 3 in the j direction, giving us a whopping grand total of -18 in the I direction plus 15 in the j direction. And there we have it as a linear combination of I and j using those standard unit vectors. Okay, so this was a long section, and I do apologize that it went so long. However, I hope you found it to be a fairly easy section. Hopefully the homework for this will not give you too much trouble. A word to the wise on the homework. We need to be cautious with that. On WebAssign, I apologize in advance for WebAssign, just saying. But just make sure that you're submitting your stuff regularly. It's very frustrating when you put in a whole bunch of answers and try to submit and they don't get accepted. So just submit your answers regularly so you don't have to go back and continue to re-enter those. All right? Okay, guys. Thank you so much. If you have questions about this, please do let me know.